What's going on, guys? The main focus of this video is going to be the random walk model, and we're also going to cover transformations that we can use for a time series model, as well as different metrics we can use besides the mean squared error. What is a random walk model? So we're going to start off with an example. So say we had a stock price that started at $50. So at time interval 1, our stock price could either increase, decrease, or stay the same. Well, it turns out that the change in our stock price value is decided by a white noise process, which we learned is independently and identically distributed. So independent, meaning we can't use one observation to predict the next, and identically distributed, meaning there's no trends in our data, so the mean and variance stay the same over time. So let's say the first value we get from our independently identically distributed series is positive. So this would mean that our stock price would increase. And then let's say that our next value is negative. This would mean our stock price would decrease. So just because we have a positive one and a negative one doesn't give us a better indication of what the next value is going to be. So let's say we get a positive, positive. So our stock price is going to increase, increase. Now if we were to continue doing this over time, we might get a graph that looks something like this. So notice that over time, our graph is increasing. So this is what's known as drift. So drift is just going to be equal to the mean values of our white noise process. So if on average, say our white noise process produced a value of 0.5. So this means that on average, our stock price is going to increase by a value of 0.5 per the length or per terms. So over one interval, we expect it to increase by on average 0.5. Over 2 terms, we expect it to increase by 1, and then so on and so on. So if we're to make a prediction using our random walk, we can just say our predicted value at time t is equal to our value at 0 plus 0.5 and then times the length. So now the formal definition of a random walk. So a random walk is just going to be the partial sum of a white noise process. So that's just the change in our stock price. Each individual increase or decrease for the next interval is independently and identically distributed. So if it increases one term, we can't say with certainty whether it's going to increase or decrease for the next term. This means that the past time period increase or decrease cannot be used to predict the next time period increase or decrease. However, the value at time t is closely related to the value at time t plus 1. So this means that at time 50, we expect the stock, at time 0, where the stock price is 50, at time 1, we expect the stock price to be near the value of 50, so probably somewhere in this range. And then at time 1, we can say the stock price increased to 52. So we can say at time 2 now, we expect the stock price to be somewhere near the value of 52. And then at time 3, we can say it dropped back to 50. So we expect the stock price to be somewhere near 50 for time 4. And then so on and so on. Now if we were to just make a prediction from 50, notice that our variance gets wider and wider as we get further and further away. Because for instance, you could say get positive white noise 20 times in a row. So that would make a line something like this. Or you could get a white noise of 20 negative values in a row, where then your line would look something like this. So as you get further and further away, your variance is going to increase from your prediction. Solving for a random walk model. So say we're given 5 observations that start at time 0. So if we relate this back to our stock example, this would be like saying we had a stock that started at the price of 50, then decreased to 48, then increased to 49, increased to 52, and then decreased to 51. So this decrease from time 0 to 1 would be negative 2. So this would be the same way as saying we got a white noise value of negative 2. And then from time 1 to 2, it increased by 1. So we got a white noise value of 1. And then it increased by 3. So we got a white noise value of 3. And then finally it decreased by 1. So we got a white noise value of negative 1. Now if we were to plot our random walk model, we start at 50. We went down by 2. And we went up by 1, up by 3, and then down by 1. and ended at 51. Now if we want to make a prediction, the first step would be to find our drift term. So the drift term we said is just the average of our white noise values, which is just going to be these values here. So if we average these values, so -2 plus 1 plus 3 minus 1 divided by 4, we'll get a value of 0.25. So this is the same as saying that the average of our white noise values is going to be 0.25. So on average, we expect our stock to increase by 0.25 over each interval. So if we want to make a prediction for say time 5 and time 8, we're just going to take our last known value, or our value of 51, and then we're just going to add the average amount of our drift, which was just 0.25. So we take our value at 51, plus our drift, which is 0.25, and then the number of intervals, so from 4 to 5, is just going to be 1. So our predicted value at time 5 is just going to be 51.25. Now we can do the same thing for our prediction at time 8. We're just going to do 51 plus our 51 because it's our last known value, plus 0.25. But this time it's going to be 1, 2, 3, 4 intervals away. So we'll make a prediction of 52. So now we found our predicted values, we can find our predicted standard errors. So the standard error of our predicted values at time t is going to be equal to the standard error of our white noise process times the square root of L. So this would be the standard error of our predicted value at time t. If we just wanted to find the variance of our predicted value at time t, we could do the variance of our white noise times L. So this is saying that at each increment, since the only thing that's changing is we're adding a white noise element, so from 4 to 5, it's just going to be simply the variance of our white noise process. And then if we go from 5 to 6, starting at 4, so I guess from 4 to 6, it's just going to be 2 times the variance of our white noise process. And then if we go from 4 to 7, it's just going to be 3 times the variance of our white noise process. So at each step, we're just adding the variance that we're adding from our white noise model. So then from 4 to 8, it'll just be 4 times our white noise process. But since we're mainly usually concerned with standard error, we can just use this formula here. So if we want to find the standard error of our predicted value at time 5, our first step is to find the standard error of our white noise process. So to do this, it's just going to be simply summation In the book it uses CT as to define a white noise process, minus their mean squared, and then over n minus 1. So we're going to have values of -2, 1, 3, and -1. So -2 minus the mean, which we found to be 0.25, squared, plus 1 minus 0.25 squared, plus 3 minus 0.25 squared, and then finally -1 minus 0.25 squared. And then divided by n minus 1, which is going to be 4 minus 1, we take the square root of it, and we're getting a value of 2.217. And now we have to multiply it by the length. So at time 5, it's just going to be 2.217 times the length, which is just 1. Or times the square root of the length, I should say, which is just 1. So we get a value of 2.217. This is going to be the standard error of our predicted value at time 5. And then we do the same thing for the standard error at time 8. So it's going to be the standard error of a white noise, which we found to be 2.217, times the square root of the length, which is 4, and it's to produce a value of 4.435. So now that we have our predicted values, we have our predicted standard errors, we can form our prediction intervals. So our prediction intervals. So if we want to do a 95% prediction interval of our predicted value at time 5, the formula is just going to be our predicted value at time 5, which we found to be 51.25, and then plus or minus our standard error, which we found to be 2.217, and then times our t-score. So alpha over 2 is just 0.05 over 2. And then for the degrees of freedom, whatever we use to find our standard error of our predicted value. So since we use 4 minus 1, that's just going to be our degrees of freedom, 4 minus 1. So we can find this in the chart, 0.0253, and we'll get 3.1824. So if we're going to plug that in, we get a prediction interval of 44.19 to 58.31. So if we want to plot this, so at time 5, our predicted value is going to be 51.25. So that's going to be right about here. Now our prediction interval is going to be from 44.2 to 58.3. So 44.2 to 58.3. So it's saying at time 4, our value can fall anywhere within this range. And the yellow line is just going to be our predicted value. Okay, so now we can find the prediction interval for time 8. So we want to find the 95% prediction interval of our predicted value at time 8. It's going to be our predicted value at time 8, which we found to be 52. And then plus or minus our standard error, which is still going to be the same value. Oh, no, it's going to be 4.435. And then times our t-score, which is the same value, 3.1824. And it's going to produce a prediction interval of 37.89 to 66.11. So if we want to draw that on the graph, we could do something like this. So notice how the range is getting bigger and bigger as we're getting further and farther from our last known value. And then our predicted value would be 52. Identifying a random walk. So there's 3 steps to check if our series is a random walk. The first is to check if our series, it should be non-stationary. So this means that either the mean or variance change over time. So if we look at our plot above, we can see that our variance is getting wider and wider over time. So that already fails non-stationary of equal variance. And then if our drift term isn't 0, then our mean's also going to be changing over time. Okay, the second check is going to be that our difference series should become a white noise. So our difference series above is just going to be these 4 values we created. So since a white noise is the partial sum of a white noise, since a random walk is the partial sum of a white noise process, so we're adding a white noise to each of our individual increments, that our difference series, which is these 4 values, should just be all white noise values. And finally, the standard error of our original series should be greater than the standard error of our difference series. So we already found the standard error of our difference series to be equal to 2.217. It's our white noise. So this number should be less than our original series, which was just values 50, 48, 49, 52, 51. And we're going to find the standard error of these values. We would get 1.58. So since this number is not less, we can say that this is evidence against our series being a random walk model. So we would say that our series is probably not a random walk model. Transformations of a time series. So on the plot, we have a series with an increase in trend, and the variance seems to increase over time. So we just learned that one method we can use is we can take a different series. We're going to take the y of t minus the y of t minus 1. Now the results of creating a different series is that we're ultimately going to be able to remove the trend, but we're still going to have this increase in variance. So with a different series, we remove trend. Now in linear regression, we learned that one way to remove unequal variances, or heteroscedasticity, was to apply the natural log to our dependent variable. So we can do the same thing in time series. So we take the log of our series, we're going to be able to remove the unequal variances. But now the trend's still going to stay. So with the log of yt, we're going to remove unequal variances. And then finally, a different series removes the trend, and the log removes the unequal variances. So if we take the log of the different series, we're able to remove both the trend and the unequal variances. So why would you want to do this? So generally it's easier to model once these elements are removed from the time series. Metrics. So we learned in the linear regression chapter that we can take a portion of our data, train on it, and then use a different portion of our data to test our results, to get accurate measurements for what our true accuracy is going to look like. We can do the same thing with our time series data. But instead of randomly picking observations, we're going to choose the first T1 observations and then test our data on the validation set, or T2 observations. So let's say we're given a random walk model, and the formula is going to be y at time t is equal to 51 plus 0.25 times the number of increments, or L. So this 0.25 is just the drift term. So if you want to make a prediction at time 5, we would first train our model on the first 5 observations, and then we would make our prediction. So our prediction would just be 51 plus 0.25 times 1, which is 51.25. And then at time 6, it would just be 51 plus 0.25 times 2, which would give 51.5. Now we can find our error term, which is the same as residual, so observed minus predicted. So it'd just be 53 is our observed value, and we predicted a value of 51.25. So we get a residual of 1.75. And then for the next observation, it would just be observed minus predicted, so 52 minus 51.5, and we get a value of 0.5. So 1.75.5. So now one metric we can use besides mean squared error is the mean error. So the mean error is just going to be the average of our residuals. So the summation from t is equal to t1 plus 1, such as here's our sum of our t1 values, and then plus 1 means we're just going to start at our validation set, and then we're going to continue until all the observations. So we're going to sum over these two observations residuals. So the mean of our errors is just going to be 1.75 is our first residual, and then our second residual is 0.5, and then divided by the number of observations in T2, which is just 2. and we're getting a mean error of 1.125. Now mean percentage error. So the errors are going to stay the same, and this yt is just going to be the observed value at time t. So our residual is 1.75 divided by our observed value, which we can see is 53. And then plus, and then the second residual, which was 0.5, and then divided by our observed value, which is 52. And then times 100 over T2. So T2 is just the number of observations we're using our validation set, which is 2. And this will produce a value of 2.13%. Now, mean squared error. So this is one we should be pretty familiar with. And with the degrees of freedom, we're just going to use T2. So the error squared is going to be 1.75 squared plus 0.5 squared, and then divided by 2. And this would produce 1.656. And mean absolute error, we're just going to take the absolute value, but since both our numbers are positive, it won't change our estimate, so it's just going to be 1.75 plus 0.5 divided by 2, so we'll get 1.125. So the mean absolute error, since all the numbers are positive, is going to be the same as our mean error. And then finally, we can do mean absolute percentage error, which is going to be 100 over the number of observations in our validation set, which is 2. And then times the summation of the absolute value of our errors, which is 1.75, over observed value, which is 53. And then plus the absolute value of our residual over our observed value, which is 52. And this will produce a value of 2.13%. So that wraps up this section. I hope you enjoyed, and I'll see you next time. Thanks.